Right, welcome to curve sketching, and this is going to be a relatively short podcast because, well, I just again did a problem that we'd just done. So so now I don't have too much time. All right, but we're going to finish off this problem. Remember, we already did the first derivative test, and when we're looking to justify our relative maxes and relative mins, make sure that you don't just include a pretty picture like this one. Right? That can be useful for helping you remember that if your second derivative is positive, it's concave up. Look at his smiley happy face. And if the second derivative is negative, it's concave down. Look at his surly looking face. But you need to make sure you explain it, your reasoning. And you need to explain it completely using your first derivative test for relative max and mins. So there's a local maximum at 0, 4 because our first derivative is greater than 0 for all x in -infinity to 0. And our first derivative is less than 0 for all x in 0 to 2. So we go from increasing to decreasing. There's a local minimum at 2, 0 because our first derivative is less than 0 for all x in 0 to 2. And our first derivative is greater than 0 for all x in 2 to infinity. Right? So you're changing signs again from negative to positive. Right? From decreasing to increasing, that's going to be a relative min. We can also, so we have possible extrema at 0, 2, and we tested those out on the other page. However, you could also use the second derivative test. Right? So you take the second derivative and you plug the values in. Right? So here, because the second derivative at x equals 0 is negative, the graph is concave down, and therefore 0, 4 is a local maximum. So there's a perfectly good explanation for why we have a maximum at 0 using the second derivative test. Right? And we can do the same thing with the other critical point. So the second derivative for 2 would be positive number. So because the second derivative at x equals 2 is positive, the graph is concave up, and therefore 2, 0 is a local minimum. Right? So for a second derivative, if it equals 0, for critical points from the first derivative, the second derivative is inconclusive. So if you plug in a possible critical point and you get 0 using the second derivative, then it's inconclusive and you need to do a sign chart. All right, just a reminder, the second derivative test, if your first derivative equals 0 and your second derivative is positive, then your function has a relative minimum at c. If the first derivative at c is 0 and the second derivative at c is negative, then your function has a relative maximum at c. That's because if you're going to be concave down, right, it's going to be your second derivative is negative, you're going to be a maximum. And if you're concave up, right, then your second derivative is positive, you're going to be a minimum. Right? And if both the first derivative at c and the second derivative at c is 0, your second derivative test is inconclusive and you can't use that test. And here's our function graphed. Right? So we have our x-intercepts. Notice that we have a inflection. So if we look here at our graph, at our table, I should say, whenever y is 0, right, that's going to be an x-intercept. So right here we have an x-intercept. We have another x-intercept over here. Right, so if you're reading the table, just so you can understand these. Right, and then if x is 0 and y, whatever y is, that's going to be the y-intercept, because we're looking just at x and y here. This is straight from the function. Right? And now if we look over at the first derivative, right, we have a critical point. Right? So the value of the first derivative is 0. When is it? At 0. All right? So that means that this here is going to be a local maximum, right, because our first derivative is 0. We have another place where our first derivative is 0. Well, it's not a local maximum because our first derivative is 0. It's a critical point because our first derivative is 0. It's a local maximum because we did a sign chart, and we showed that it goes from increasing to decreasing. And then we have a local minimum. So notice here we have another critical point. And so that occurs when x is 2. And so 2, 0 is going to be a local minimum. Right? So 2, 0 here is a local minimum, and 0, 4 is a local maximum. Right? And then we have our inflection point. So our inflection point occurs where our second derivative, or possible inflection point occurs where the second derivative is 0. We know it's an actual inflection point because we had a change in sign. It went from negative to positive, so that means your function is going to go from concave down to concave up. And you can actually see that really well in the chart here. So here's where our second derivative is 0. Right? So notice these are all negative values. Right? So that means you're concave down. These are all positive values. These means you're concave up, because that's looking just at the second derivative. Right? And so your second derivative is 0 when x is 1. And then you just plug in the function. So 1, 2 there is the inflection point. All right, and there we have our graph. So you can see we changed concavity right there from concave down to concave up. All right, I think this one is in your notes. All right, so let's look at one more problem, and that's going to be it for my podcast. All right, so determine the x and y intercepts of our function. All right, so you're going to have an x-intercept where your numerator is equal to 0, right? Because if you set the whole thing equal to 0 and multiply by x cubed, you're still going to have 0 equals 7x squared minus 7. All right, so we set 7x squared minus 7 equal to 0. We can factor out a 7, right? You can divide both sides by 7, and you can see certainly that x squared minus 1 is factorable. And so we have two x-intercepts, one at 1 and one at negative 1. All right, so to find our y-intercept, we plug in 0 for x. And that's a very bad thing to do because we have 0 in a denominator. So there is no y-intercept. And why not? Because we have a vertical asymptote there. All right, so if we set our denominator equal to 0, we see that x equals 0, we have a vertical asymptote. If we take the limit of our function as x approaches infinity and negative infinity, we see that we have a horizontal asymptote. Right? So 7x squared minus 7 divided by x cubed. If we divide everything by the highest power of x, looks like I divided 1 time and then 2 times, just to make things more interesting, instead of just dividing by x squared. X cubed. So I could have divided by everything by x cubed, which would have been a little faster. Instead, I divided by x once, and I have, actually, I'm sorry. I used something I hadn't taught you yet. I need to erase that. So as I'm looking over, it's like, I see what I did, but I haven't taught you that. Right? So I'm going to solve out the horizontal asymptote using a limit, and not something I haven't taught you yet. It's my next lesson, however, because I decided to do this first and then do my next lesson. I guess I should have flipped it. So if I divide everything by x cubed, right? So I have my 7 divided by x cubed because that's the highest power of x, right? If we can do this whenever we have a rational function and a limit going to infinity, right? We can divide by the highest power of x and see what we have, because that will be the same as our original function. So this would reduce to 7 divided by x minus 7 divided by x cubed divided by 1. All right, so if we've got 7 divided by x, we've got something that's not changing, being divided by something that's growing and growing and growing, that's going to go to 0. So this is just 0 minus 0 over 1, and that's just 0. So y equals 0 is a horizontal asymptote. So there I use the old-fashioned limits, right? I will need to probably show you another way to take limits very, very soon. All right, so determine the first and second derivative of our function. All right, so we'll take the first derivative. So dy dx this would be the quotient rule. All right, so our numerator is 7x squared minus 7. The derivative of that is going to be 14x. And then our denominator is x cubed, and the derivative of that is 3x squared. All right, so for the quotient rule, we have the denominator, which is x cubed, times the derivative of the numerator, so that's 14x, minus the numerator times the derivative of the denominator. So the derivative of the denominator is 3x squared, so and then times that by 7x squared minus 7 all over x cubed squared. All right, so let's simplify this. Our derivative is equal to, so we'll distribute and then combine like terms. So we have 14x to the fourth minus, that horrible looking number was a 7, almost looks like a 2. So that's minus 21x to the fifth, and then minus a negative, that'll be a plus 21x cubed, all divided by x to the sixth. And I hope you see you can reduce all of these. I could factor out an x, actually I could factor out a 7x cubed. Well, it's really, I can factor out the 7, doesn't make much of a difference. What the heck, I'll just factor out the 7. But I can factor out the x cubed and reduce. So that would leave this as being 2x minus 3x squared, and then plus 3. Yeah, I can divide by 7 by 21. All divided by x to the 6. Pulling out the 7 wasn't the most important thing, but we're going to set it equal to 0, and so that might be helpful. That will cancel. So that means that our first derivative is equal to 7 times 2x minus 3x squared. You know, let's rewrite these in order. That's kind of visually ughy. I'm just going to actually put the 7 back because I got to take the second derivative, and it's not going to really help me to have the 7 pulled out. Later on, we can pull out the 7. So this would be 21x squared plus 2x plus 3, all divided by x cubed. So let's take the derivative of that. So we have d2y divided by dx2, right, our second derivative notation. And no part of me thinks that's going to be enough room to do this. So let me actually expand the page and take the second derivative. So that's, I'm going to write that down, negative 21x squared plus 2x plus 3 divided by x cubed. We're probably going to need more space. Let's just see if I gave myself space over here. Yes, I did, but is there an error in my, did I make a mistake when I don't see a mistake on this one. Is there a mistake in my notes when I was typing or doing whatever? 7x squared minus 7, that's just going to be 14x. That's fine. And then x cubed is 3x squared. Oops, but I wrote 3x cubed. Dun, dun, dun. I just can't copy. All right, so let's fix that. So, you're probably, hopefully you're sitting at home going, Ms. Michelle, I got a mistake. That's 3x squared. Boop. All right, so now this is going to be plus, this one is the error over here. I'm going to erase a little farther. So that's supposed to be minus 21x to the fourth plus 21x squared. There we go. So that's going to change our derivative. We don't have 3 terms. We only have 2 terms now. So negative 7x to the fourth plus 21x squared divided by x to the 6th. And again, we can factor out the x squared. I'm just going to leave the 7 there. Negative 7x squared plus 21 divided by x to the 6th gives us our real first derivative, which is a good thing I didn't do that derivative on this page. I turned the page to realize I had an error. I can't seem to copy. Negative 7x squared plus 21 divided by x, oops, I forgot to cancel these, x to the 4th. All right, let's do the second derivative on the next page. There we go. That one's right. All right, so our second derivative, I'll just put Yeah, I'll put this notation. You should get used to seeing it anyway. Oops, we got to squeeze the 2 in there. d2y over dx2. All right, so we're going to take the second derivative here. So again, it's quotient rule. All right, so u is negative, our numerator, negative 7x squared plus 21. The derivative is going to be negative 14x. And then the denominator is x to the 4th. The derivative is going to be 4x cubed. All right, so that's going to give us, for our derivative, negative 14x times x to the 4th, and then minus 4x cubed times negative 7x squared plus 21. Boop. There we go. All right, so on all over x to the 4th squared. So this is negative 14x to the 5th. That's going to be plus 28x to the 5th. And then minus 84x cubed. All divided by x to the 8th. All right, and again, we could reduce. All right, so I'm just going to write the final answer here. All right, so we're going to actually, let's combine our like terms, right? I didn't make a mistake this time, right? I wrote down the right thing. 4x cubed, yeah, that looks good. And that is negative, that looks okay. All right, so this is going to be, if we combine those, that's going to be 14x to the 5th minus 84x cubed, all divided by x to the 8th, and then we could factor out the x cubed and reduce. So final answer on the second derivative is 14 x squared minus 84 divided by x to the 5th. That's not work. All right, so we'll set that equal to 0 and solve. And I think I'm just going to set this problem up because I'm probably going to run out of time. It's going to be a longer podcast than I wanted it to be. All right, so let's complete a sign chart analysis in class. We've done all that background work, not a whole lot of new stuff, but I think I can maybe do this a little faster in class, and I can go over it and answer any questions rather than waiting. So this was just kind of like some review things for you in this particular podcast, but we'll do more things in class on Monday. Thanks for watching the podcast. Bye.